Hello and welcome back to AGT STEM. Today we're going to be watching a video about cesium. So, without further ado, let's hop to it.
If you remember back to the last cesium video, Pete and Neil tried to launch a bit of cesium metal into water with the small metallic collider, and they had a few problems with surface area and the cesium still being stuck in the glass as well. What I've been asked to do today is take this ampule of cesium into this piece of machinery here, which is one of our glove boxes, try and get it out of the glass so that we can put it in as is.
Cesium has quite a surprising use. It's used to measure time. I don't know if you've ever thought about it, but you could define 1 second as a fraction of a day. 1/60th of a minute, which is a 60th of an hour, which is then a 24th of a day. But the trouble with that is that you'd never be able to tell whether the Earth was going slower or speeding up, because the length of the day would change and you wouldn't notice it. So scientists have to have an independent way of defining the second, and this is where cesium comes in.
And so now here the cesium is going in as well. Right, so we'll shut the port door.
So the way that physicists define the second is in terms of microwaves and the frequency of the microwaves. We need a standard, something that can define a radio wave very, very precisely, and this is where cesium comes in.
So what I need to do now is open up this door here.
The point about cesium is that it's a big atom. It can absorb microwaves. The absorption of the microwave causes an electron to move from one energy level to another. And the advantage of cesium over all other materials is that this frequency is enormously precise.
It's pretty cool, it's really good. It's kind of, I don't know, a sort of really pale gold colour. It's still molten at the moment.
It's rather like tuning a radio. I don't know if you've ever tuned a radio, but as you turn the knob, sometimes you don't have to be very precise. You can put it almost anywhere and you get your favourite station. But there are some stations where you have to adjust it very, very accurately, and there's just one tiny place where you can get the right radio station. And cesium is like that. It defines the frequency very, very accurately. If you don't hit it right, it doesn't absorb the radio waves. And so you can use it as a standard to make sure that everybody has exactly the same frequency of their microwaves. And then once everybody's got the same, then it's quite easy for everybody to agree that they will count a certain number of waves as being a second.
We're going to store the cesium under oil so that it doesn't react with air when it comes out. So this is ready now for Pete to chuck it in some water, and we will stand very far back when he does it.
So we've got cesium, we've taken it out of the ampule. Neil did that the other day with Debbie in her glove box. They've put it into a small plastic weighing boat and immersed it in oil so it can't react with the air. Now what we need to do is a very technical operation, which is to punch a hole in the plastic boat so that we can lift it out with a piece of string to drop it into some water. I've got my friend Dr. Red. It's always good to be very, very careful when you do chemistry like this, so just in case something goes wrong we have the safety procedures ready for us in case we get surprised. So now Neil's going to pass a piece of string through the hole so that we can put it on the end of a rather long fishing line so that we can drop it into water. So this is Neil's new device. It's a very, very fancy erection. Essentially we've used a laboratory stand and we have an eyelet. So this is just to act as a point with which we can raise up our cesium on a piece of string. At the moment, the cesium, you can see the lovely gold colour. Would you believe me? It's melting. Look at it. Oh yeah, it's very warm here today and the cesium's melted. So we're just going to try and freeze it again. Well, we're going to try and refreeze the cesium by cooling it with liquid nitrogen. Okay, everybody, be careful. So we have our cesium under oil. We now need to lift it up using the new device and then drop it in the water, and let's see what sort of chemical reaction it does today. Everybody ready? Neil?
Yep.
Well, quite a spectacular reaction. As the cesium reacted with the water, gave away its electron, off she goes as cesium plus.
Awesome. That's pretty good.
Yeah, it's great. You know, when Debbie and Neil took the cesium out of the ampule, they were really, really good for us because they gave us a really large surface area so it could react quickly as soon as it went in the water, generating all that lovely hydrogen ready to explode and make a bang. Great, good chemistry.
Well, the reason that cesium reacts so violently is that it is a very large atom. So an electron can be removed very easily. In fact, if you dissolve cesium in water, on a very short time scale, a millionth of a second or so, it dissociates into cesium plus and an electron. And the energy of the electron interacting with the water is enough to separate the two. And once the electron is in the water, it then reacts with the water so that H2O dissociates into a hydrogen atom and OH minus. So in fact what you're making is a cesium salt, which is rather like caustic soda. It's a strong alkali, and hydrogen. And it is the rapid formation of hydrogen gas that causes part of the shock of the reaction, and then the hydrogen.
That's pretty cool. All it has to do is, like, one of the electrons gets removed, which is pretty easy to do with cesium, and then it produces hydrogen, and then it goes boom.
Will usually catch fire and react with the oxygen in the air to give you a small explosion, or a big one, depending how much cesium you've used.
Thank you so much for watching, and we'll see you next time. Stay smart. Bye!